This presentation introduces the main types of transmission line used in high-frequency engineering. The purpose of a transmission line is to guide the signal from a source to a load with low loss and with some shielding to avoid leakage and interference from outside. So shown in red is the power flow from the source to the load, and the other two arrows are there to imply that usually there are two conductors and there's a forward-going current and a return path for the current. So the most common kind of transmission line is a coaxial cable. You can see this has a cylindrical outer shield, typically grounded. It has a centre conductor and normally some kind of insulator to separate the inner conductor from the outer. So the kinds of cables you might use in an undergraduate laboratory typically have a braided outer shield, and they have, for example, BNC connectors. That's a bayonet kind of connector which you push on and twist. When we consider how a coaxial transmission line works, we need to look at the fields in the transmission line. Shown in green are the magnetic field lines, which form circles around the centre conductor. Shown in red is the electric field, which is perfectly radial. Now, it's a very important concept in transmission line techniques to realise that the magnetic and electric fields mean that there are inductance and capacitance which are distributed all the way along the transmission line. So in the case of a coaxial cable, it's very well known that you have to talk about a capacitance per unit length. So when you're using coaxial cables at lower frequencies to make measurements, you have to be careful about how that capacitance might load your circuit. Often, therefore, you use things like oscilloscope probes at lower frequencies. In the high frequency world, what happens is that you have also the important inductance per unit length, and the two work hand in hand to create what's called a characteristic impedance, Z0 or Z0, which is the square root of the inductance per unit length divided by the capacitance per unit length. So actually, in a high frequency transmission line, the wave is propagating down the transmission line as a combination of electric and magnetic field. Coaxial transmission lines, depending on the type of connector, are usable up to 110 gigahertz. It's very important to realise that these are ideal for broadband, for wideband components. That's a fairly sophisticated topic, but the reason is that the coaxial transmission line has what's called a pure TEM field, transverse electromagnetic. If you were to cut all the way at different points along this coaxial transmission line and look at the field pattern, you would see it looks exactly the same. It's that consistent electromagnetic field pattern all the way along the line, which is referred to as TEM propagation, enables this to work over a wide frequency range with the same parameters, and therefore you can use it, for example, in measurement equipment. One interesting example of the use of coaxial transmission lines is the use of these ribbon cables for high-speed data transmission in, for example, a computer. And you can see in the cross-section here that what appears to be just a simple ribbon cable is actually containing a number of coaxial transmission lines, so you can get very high-speed data transmission. This is the blue ribbon microcoax from Tyco Electronics. The next kind of transmission line, which is very common in making circuits, is called microstrip. And this consists of what's called a substrate, something similar to a printed circuit board, but with special materials for low loss at high frequencies. We have one side of that substrate completely metallized and acting as a ground plane at the bottom. On the top, we place our signal conductor here. So this is essentially a transmission line made on what looks like a printed circuit board. That's very convenient for making circuits, and this example shows the inside of a satellite TV low noise block. We'll study this in greater detail in another presentation. The maximum frequency that you can use microstrip to depends very much on the kinds of materials you choose and the size of the microstrip line. One advantage of microstrip is that it's fabricated just like a printed circuit board by photolithography using photomasks, so it's cheap to make. Secondly, you can easily solder on components and make all kinds of circuits. However, you do need to be careful because the losses in microstrip are quite high for a number of reasons, so you don't get particularly good performance. A third kind of transmission line is either a twisted pair of conductors, as shown in the bottom right, or a nice perfectly parallel pair of conductors, which is often called a Lecker line. So the twisted pair is actually very common in data communications, in things like the Ethernet. So you may have heard of a UTP cable, for example, which stands for unshielded twisted pair. So this kind of arrangement gives fairly minimal confinement or shielding of the signal and is generally used only at the lower frequencies. But one noticeable example of a Lecker line on the bottom left is the FM ribbon cable that's often used in radio systems. The fourth kind of transmission line is the hollow metal waveguide. These are extremely low loss and can handle high powers. They're typically usable from about 1 GHz to 325 GHz. Although in fact, fairly recently, waveguides beyond 1 THz, 1000 GHz, have been made and put into commercial products. These have very complicated electromagnetic fields which are not TEM. So it's very difficult to actually understand in detail the propagation parameters of these hollow waveguides. So firstly, the rectangular metal waveguide is a single metal pipe, so it can't possibly transmit DC. Remember, you need a return path for the current to transmit DC. So these kinds of hollow waveguides have what's called a cutoff frequency below which signals cannot propagate. And in fact, the way a hollow metal waveguide propagates the wave is very, very similar to the way an optical fibre operates. In the optical fibre, you have a core and a cladding with different refractive indices, and you have total internal reflection, so that the light beams will bend and reflect backwards and forwards down inside the core of the fibre. In the rectangular metal waveguide, you have the same kind of reflection, but now you have metal sidewalls, and so you can think in terms of a pair of waves travelling down inside the metal waveguide, bouncing backwards and forwards, reflected off the metal sidewalls. And the actual field pattern that propagates down the rectangular waveguide is a very complicated field pattern, which is the sum of this pair of waves, both reflecting down the metallic walls at this critical angle. So the fundamental mode of propagation is referred to as a transverse electric mode. This field pattern is showing the electric field across the inside of this hollow waveguide, and you can see it's all standing perfectly vertically, but the intensity is 0 at the two outer edges because there's a conductor there, and it's a maximum in the center. So this cutoff frequency turns out to be when the width of this waveguide is half of a wavelength. And in fact, this transverse electric fundamental mode, referred to as TE10, has a very complicated field pattern. And just to give you some idea of what it looks like, this shows the magnetic field in this TE10 mode, which forms loops inside the metallic waveguide. Now, unfortunately, if you go up to higher frequencies, you find that the rectangular waveguide starts to support even more complicated propagation modes, so-called higher order modes, which are usually unwanted, and that means that rectangular waveguides have a restricted useful bandwidth. At the lower end, you're restricted by the cutoff frequency of the fundamental mode. At the higher end, you're restricted by wanting to avoid these higher order modes. So there has to be a range of standard sizes of waveguide to cover the whole of the microwave and millimeter wave spectrum. And that's why microwave engineers very often talk about all these different frequency bands, because they actually map on to particular sizes of waveguide. So L band, for example, is 1 to 2 gigahertz. KU band, 12 to 18 gigahertz, is a particular size of waveguide, and so forth. The reason the letters are almost random is supposedly to make these fairly secret during wartime. Now, how can we actually use transmission lines to make circuits? Let's go back to the microstrip case and look at the field patterns. The electric field looks very much like a parallel plate capacitor, but with a lot of fringing fields at the edges of the conductor. The magnetic field is primarily forming loops around the signal conductor. Now, it's actually very hard to solve for these fields because some of the field is in the dielectric, in the substrate material, and some of the field is in air. Now, as we saw before, microstrip is the most common way of making circuits because it's easy to make using PCB-like etching. You can solder on components. You can make filters and matching networks just by drawing them on the computer, because the whole thing is made using photomasks. And finally, it's very important but a subtle advantage, is that the bottom of the substrate is a solid ground plane. So the ground plane takes care of itself. So as one simple example of how we might make a circuit using a transmission line, this shows at the top a 50 ohm microstrip line with a small section in between of very high impedance microstrip. So if the width is very narrow, you have much less capacitance per unit length for the transmission line, and that small section of 110 ohm transmission line looks primarily inductive. In contrast, below, if you make the width of the transmission line very wide, you get a low impedance transmission line, like 15 ohms, because you now have much more capacitance per unit length. So it's becoming more like a parallel plate capacitor. But of course, very important to remember, it's a distributed capacitance. So the short section of 15 ohm transmission line looks primarily like a capacitor. So we can make a simple inductor capacitor low pass filter just by drawing this shape at the very bottom, where you have alternate sections of high impedance and low impedance microstrip line. So we now have a way of making a microwave filter just by drawing it on a computer and making it in microstrip using photomasks. And the very important advantage now is we don't have to worry about the parasitics of lumped elements. So that's just one example which relates to a simple low-pass filter without thinking too much about how you analyse transmission line circuits. But it is very important as we realise that the design of more advanced microstrip circuits, like amplifiers, requires a full understanding of what's referred to as a distributed circuit. That's something we'll look at in another presentation.